Good morning again. Welcome to video 3 of the nervous system. You'll see we basically took the picture that we had from video 2 and now we just added on to it. So what we'll be focusing on in this video is how this nerve cell, this neuron, can talk to this one or this one. Here's why that matters. Back to how does this relate to the brain as a whole. In general, your brain just contains billions of neurons. So I've seen studies that say up to 100 billion. I've seen others that say, no, that's not right. It's more like 80 billion. So we'll just say tens of billions. So billions of nerve cells, tens of billions. So let's say here's a nerve cell, a neuron. Here's one, here's one, here's one, here's one, here's one, here's one, here's one. And so do this a few billion times, and you just have what looks like this giant tangled mess of wires. And you'll notice the wires are separate. They don't actually touch. So this nerve cell gets really close to touching this nerve cell, but it's not actually touching. There's this gap in between, and that gap can go by two names. Synapse, S-Y-N-A-P-S-E, or you might hear it called a synaptic cleft. They're both referring to the same thing. And nerve cell messages fire this way. This end over here, I know I'm dropping a lot of vocab on you kind of quickly at once, but the receiving side, or the beginning side, whatever you want to call it, of the nerve cell, the neuron, are called dendrites. So these are dendrites. These like finger-like projections over here are dendrites. And the more finger-like projections I have, the more opportunities you have to send me a message. More surface area. The long skinny part is the axon, and then these little parts right here that hold the neurotransmitter chemicals, the green triangles in my picture, neurotransmitters. These little ends also go by various names. They're sometimes called synaptic buttons. I like to call them, and this is a legit vocab word, is axon terminal, because they're the terminal, the end of the axon. So that word just makes the most sense to me. So that's what I go with. So dendrites, long skinny part is the axon, and then we have the axon terminals. Then we have to somehow get the message to go across this synapse. So the way that our brain works, and this will seem kind of weird, is when certain pathways send electricity to each other, that is a thought. So myelin sheath. In the last video, we mentioned myelin sheath. So what is myelin sheath? What does it do? So think about it for just a second. Okay, so myelin sheath speeds up the impulse of messages. How did you remember that? Like, you probably didn't know what myelin sheath was a week ago, but now you've heard it in the previous video. So how did you store that information? Well, what we do know is this might be, I know you can't read that very well, but that's 1, 2, 3, 4, 5. That little pathway of nerve cells, when those all fire, that's where you store myelin sheath. And we know that because if we stimulate that area, we can make you think about myelin sheath. Just like the example on video 1 where I gave you about surgery. If we stimulate the area, if 1, 2, 3, 4, 5, or this bundle right here is where I store my memory of the scent of, I think it was pizza I said in the video. If that's where I store it, if I shock that, you'll smell pizza. Like, it'll conjure up that memory of like, oh yeah, that's what pizza smells like. And so that's how we know that this is true. So myelin sheath, you're storing that somewhere. If a day later I say, what's myelin sheath? And you're like, oh yeah, it speeds up nerve impulses. And a day later, oh yeah, it speeds up nerve impulses. Now let's say a year later I ask you, what's myelin sheath? And you're like, I don't remember. Now there's kind of two ways that memory is explained. One of them is you no longer know what that pathway is. It's still there, like those nerve cells might still be there, but you don't know to make nerve cell 1, 2, 3, 4, and 5 fire. And so that's why you can't think of myelin sheath. And then I might say, oh, it had something to do with nerve cells. And then all of a sudden you're like, oh yeah, 1, 2, 3, 4. Myelin sheath makes nerve cells carry messages faster. Another theory is that basically we just like write over it. So yeah, it's gone. There are certain things like, what did I wear yesterday? If I thought about it, I could probably remember what I wore yesterday, especially if I went downstairs and looked in like the dirty clothes pile. But if you ask me what did I wear 27 days ago, unless I was shooting a YouTube video and I can just look it up, I don't know. And I don't think that that's anywhere in my brain. So the other idea is if something is not very important, you just overwrite it. So it's kind of like hard drive space. If I don't really use this file much, I just sort of write over that file. Those are two theories on how memory works. Okay, so my point is this. If I want nerve cell 1 to talk to 2, to talk to 3, to 4, to 5, how do I do that? So if I want nerve cell 1 to talk to nerve cell number 2, how do I do it? Well, when this electricity gets to the very end of the nerve cells, I have these vesicles full of neurotransmitters. Neurotransmitter. Now, as I said previously, I think in the last video, they call them that because they transmit messages between neurons. And so when this gets to the end, I'll do exocytosis. That green is phospholipid bilayer. That brown is phospholipid bilayer. So those can merge. There's a little bit more to it. There's some voltage-gated calcium channels and stuff, but this is good enough for us. So I basically now send some neurotransmitters across this synapse. And I also mentioned previously, there's a lot of different neurotransmitters, but the two that you are most likely to have heard of are dopamine and serotonin. And again, dopamine is on the addiction pathway. So if I'm addicted to some sort of drug, whether it's legal or not, maybe some sort of opioid prescription, and that's working on the dopamine pathway. And serotonin, when it's kind of out of whack, that's the depression pathway. So that's why we've likely heard of those. So if I look at that, and I look at this over here, if I want this guy to start like sending a message, what do I do? Well, over here, ignoring this part for the moment, essentially when this first door opens, then the next thing happens, then the next. So it's almost like dominoes. Once that first door opens, we even call it the all or none principle. You either open them all or you don't. It's either open, pump, open, pump. It's just like dominoes. If I knock down that first domino, he'll knock down the second, the third. And so either the first one falls over and knocks down the second, the third, and everybody else, or the first one just wobbles and I never send a message. The example that I give in class is a gun. I got a trigger. And it's possible, even if it's a hair trigger, that I have to apply some pressure to it to get it to fire. It's possible that I provide, 0.01 pounds of force and it doesn't fire. 0.02, 0.03, 0.04. When I get to 0.05 maybe, and I have no idea if that's a realistic number, but at 0.05, all of a sudden it fires. Okay, no matter how hard I pull the trigger, as long as it's more than 0.05, the gun fires 100%. So it's not like I could just sort of kind of shoot this guy, or if I really do want to shoot him good, I'm like, I'm going to pull the trigger extra hard. No, it's either hard enough to fire the gun 100% or it's not and you fire 0%. So how do I get this nerve cell over here to start sending messages? I have to somehow start opening these doors. Well, here's a door, and it's the same color as this because it's a gated sodium ion channel. Now, it's not voltage gated, it's chemically gated. A chemical is going to open it up. What chemical? That one. Serotonin, dopamine, or some other neurotransmitter. So now, when this neurotransmitter gets across, it has the right shape to fit that receptor, and the door opens. When the door opens, there's a bunch of sodium outside, and that sodium will rush in. And that's the beginning of trying to get this nerve cell to carry on the message. So electricity, chemical, electricity, chemical, going to another nerve cell, electricity, all the way across. And that's how we send messages. Okay, cool. Well, how does this relate to psychoactive drugs? Again, that psychoactive drug might be legal or illegal. Okay, so in this picture, let's see. There we go. That'll be a good size for y'all. In this picture, we're going to see something. I sent across some serotonin. So those little green balls there, are green circles, are serotonin. they go across, they hit these receptors. Those receptors in purple right there are these receptors that I have in brown up here. And when I hit those receptors, I open up the doors, and this nerve cell fires. Let me make sure you guys can see that, okay? Yeah, that'll work. And it looks like I must have started at about 10:55. Okay, so now what you'll notice is this. If I send that serotonin across and it hits that receptor and the door stays open, as long as that serotonin's there, that door stays open. Serotonin is acting as a doorstop. And basically, if here's this door that closes on its own, and I stand in the doorway, as long as I'm there, the door's open. As soon as I move, the door closes on its own. So serotonin is acting like a doorstop to keep the door open. This particular gate doesn't have any serotonin holding the door open, so it's closed. Okay, so what that means is throughout here, I'm just going to draw them as X's. I also have enzymes whose job it is to either recycle the neurotransmitter or destroy it. So basically, when serotonin goes across, there are enzymes that will grab serotonin and then recycle them. So this X right here might go over, grab that serotonin, and send it back into the nerve cell. As soon as he removes it, the doorstop is gone, that closes, and now this nerve cell quits firing. And then I can just keep recycling that serotonin over and over. Okay, well, why does this matter? Well, let's say that for me to feel happy enough to where I'm not suicidal, it might not be a good day, but it's not like I'm thinking of ending it all day. And I'm not trying to make light of suicide. It's just, there's happiness, like I'm having a great day. There's, yeah, it's a day. There's, this day sucks, but you know, you can have a lot of sucky days and you never actually consider ending your life. So for you to be happy enough to just not be suicidal, let's say that this pathway, 1, 2, 3, 4, 5, this part of your brain, when it fires, if you just have an average day's happiness, like not great, not bad, you know, I got food, I got shelter, you know, it's cool. Let's say that this is firing, say, once every second, you know, something like that. Okay, well then if it fires a little bit faster, then I might feel more happiness. Now it's like, hey, today's a good day. Or it might be firing a little bit slower, and I'm like, yeah, I mean, the day will come to an end, and then tomorrow's another day. I'll get through this, if this is firing slower. So when this nerve cell talks to this nerve cell, that somehow generates this, like, happiness. How? We don't know. The thing that's kind of odd about the nervous system is we know all these details, like 70 millivolts and all these different gated channels and what chemicals are going across, and we can measure all kinds of different things, but then, like, how does it in the big scheme of things equal happiness? Or when I close my eyes and I think of my wife's beautiful face, how is it that, like, when all these nerve cells fire, there's like a picture of somebody's face, like where's the screen, or this memory that I'm thinking, like, where is that? And so we kind of know the details without knowing the big picture. Almost like if we had a car and it was completely disassembled. We know all the details. I can tell you how many bolts we have, how big they are, you know, all these different filters and how big they are and how much they weigh and all that. But then, like, how do you put it together? It's like, I don't know. I don't know how to weld a car, and there's no instructions. So I know the details, but I actually don't know that that thing right there powers that thing right there, and it moves this belt and, you know, some piston or whatever. So we have these little guys in here that either recycle or destroy the neurotransmitter. Okay, so what if I don't send across enough serotonin? Let's say I'm supposed to have this much happiness. You know, I'm releasing this much, 100 units of serotonin per second, and that's average happiness. Well, what if instead of releasing 100, I release 90? Well, now I'm not as happy as average, so, or 85 or 80, now I'm kind of depressed. Or what if I secrete the right number of serotonins, but I've just got too many of these purple X's. They're just too good at intercepting serotonins and bringing them back. In fact, that serotonin might not even make it all the way across before he's intercepted by this guy and sent back for recycling. So then I'd still, same effect. The message isn't getting across, These nerve cells aren't firing as often as they're supposed to, and so now I feel depressed. So what can I do about that? Well, as far as a drug, I can take Prozac. So let's say that these are your nerve cells on the left here. You're sending across a message, and only about 1 out of 4 receptors, it looks like, are actually receiving the message. And let's say that results in depression. Well, we can give you Prozac or Zoloft. They're slightly different chemicals. They'll likely have very slightly different side effects, but they accomplish the same task. Prozac and Zoloft, you don't have to know the name of this, but they call them SSRIs, selective serotonin reuptake inhibitors. So they're inhibitors, and what do they inhibit? The reuptake. Serotonin is sent across, and then I'm supposed to reuptake it to send it again. I'm recycling it. They're selective for serotonin reuptake. So Prozac blocks these guys that are the Broca's area, that are the recyclers. So now I might still be sending across the same amount of serotonin, and maybe that's not quite enough for me to have, average happiness. But if I can sort of interfere with these guys a little bit, now more serotonins get across, right? If I'm a quarterback and I can throw a ball every 1 second to a receiver and I want them to catch it, great. But if there's just too many cornerbacks covering them, then what can I do? I can either, get more receivers going out, or I can get rid of some of the cornerbacks. We're getting rid of some of the defense, some of the cornerbacks. And so now more of the serotonin is getting across, and so hopefully I don't feel depressed anymore. Well, the consequence of that is, okay, now I'm kind of back up here to 100. So if I'm at 100, something great happens, then maybe I go up to 110. I'm like, woohoo! Or something bad happens, I'm like 90, 85, 80. That's not good. And so Prozac is supposed to even that out. So if something tragic has happened in my life or whatever, and I need just a little something to get me over the bump, then I might take Prozac or Zoloft or something. Again, the difference between Prozac and Zoloft and the others, there are several others, I just don't know the names. Because they're slightly different chemicals, they might have slightly different side effects. And so with different people, the side effects might be different. Even though they're accomplishing the same thing, it might be like, yeah, but Prozac, the side effect is this and it's minor, whereas Zoloft, the side effect is this, and for me, that's major. But they're both blocking the reuptake. The tricky part is other parts of our brain, not related to happiness, also run on serotonin. Prozac doesn't know who to block and who not to block, so it can affect other parts of my brain. And so that's why there are other side effects. If you're taking Prozac and you're taking too much, then patients will describe certain symptoms. So if I'm a psychiatrist, I prescribe you, based on how big you are, like how much you weigh, I'm going to give you a dosage of Prozac of this many milligrams or micrograms or whatever. So take this pill once a day or something. Come back, it takes several weeks for Prozac to kind of be in your system, so to speak. So after we talk, it might be a month and a half or whatever later, and maybe you visit every week or something, but 4, 5, 6 weeks later, we're kind of watching it. And after 4, 5, 6 weeks, you might say, well, I'm not as depressed as I used to be, but here are these other side effects. And a psychiatrist can be like, those are side effects of too much serotonin getting across. So let's cut your dose. Or they might be like, yeah, you still sound kind of depressed. We need to just up your dose a little bit. So they give you a base dose, and then when you start describing how you feel, they'll be like, oh, it sounds like too much, let's reduce it. Or it sounds like too little, let's bring it up. So it might take them several months to dial in your dose of Prozac or Zoloft. So it's kind of a slow process. You do have to stick it out. Okay, now, why not just give everybody Prozac? Or wouldn't the symptoms of too much Prozac just be like, excessive happiness? I mean, that sounds pretty good. It's not the case. So too little Prozac is depression, but way too much, and now you start having trouble telling the difference between reality and non-reality. That's called schizophrenia. So if I'm not schizophrenic, and let's say I go into my job and my boss says something, and I'm like, I wonder what he meant. I wonder if he's upset with my performance or something like that. And I think about it. I might try to, make some adjustments. The next few times I see my boss or do a presentation, I might kind of like spend a little bit more time getting ready. You know, I want to impress my boss and keep my job. So that's pretty logical. If I'm schizophrenic though, and there are different types of schizophrenia, I'm going to describe paranoid schizophrenia. A paranoid schizophrenic might read into that a whole lot, and they're like, oh, my boss doesn't like me. Okay, could be true. Maybe your boss doesn't like you. That's pretty normal. Yeah, my boss wants to fire me. Could be true. That's a normal thought. Is there other evidence for that? Maybe, maybe not. The next thing you know is you're like, yeah, I think my boss wants to fire me. So now I think my boss is spying on me. You know, I heard a car drive by. I think that was my boss, and he's trying to like catch me doing something in my house so that he can fire me. Or, you know, now he's tapping my phones at home, or he snuck into my garage and he's putting surveillance equipment, you know, like that's kind of unlikely. So the schizophrenic brain, though, all of a sudden that seems like a legit concern. To my non-schizophrenic brain, I'm like, my boss isn't climbing around in the attic putting in cables. He might not like me. He might be thinking about firing me. I maybe should step up my game a little bit. That's all normal. So extra serotonin is linked to schizophrenia. So too much of Prozac or Zoloft might kind of give you schizophrenic type symptoms. So the moral of the story is basically stick with your doctor, do whatever they say, and don't take someone else's medication, and don't give this to your friends. So your doctor should be prescribing it, and if your doctor says you should take one pill, take one pill. If she says take two, but don't take three unless she says take three. There are medical professionals there to help you out. Okay, how does this relate to illegal drugs? Well, first of all, here's a microscopic image of a thought. So that's a nerve cell right there. You can see the vesicles. Mine are green on the board, but these are stained purple. That purple stain is neurotransmitter. So those are little purple stained vesicles full of neurotransmitter. And that little bitty gap right there, that's the synapse. So you're seeing a nerve cell here and a nerve cell here, just like nerve cell and nerve cell. And so neuron and neuron, pow. So that's a nerve cell talking to another one. So that's what a thought looks like, which is kind of trippy. The next picture is cocaine. So we aren't going to talk about like all the different types of illegal drugs. We'll just pick cocaine. So cocaine gets me high, but it's addictive, and you know, it might force me to do all kinds of bizarre things that I wouldn't normally think of doing. You know, I would never steal. I'd definitely never steal from like my own parents. But if I have a coke addiction, then all of a sudden that becomes like a viable option. So how does that happen? Well, the way that cocaine works, if you look at the diagram, again, back to the serotonin diagram where we have Prozac, cocaine works in a similar manner. It's blocking the reuptake of dopamine. Again, I told you earlier that dopamine is linked to most addiction pathways because the pathway where we get pleasure from food, sex, water after you're really, really thirsty. You know how good water tastes if you've been like outside working all day, or how good food can taste. You get that reward of like you're hungry, and then you get a Snickers and you're just like, that's so much better. Just like the commercial says. Well, that's what's happening here. So same thing, I've got a nerve cell, it's sending across DA, dopamine, and that's hitting maybe 1 out of 3 receptors, and so I'm having a normal amount of, you know, like pleasure, just being alive. Well, with cocaine, cocaine blocks the reuptake of dopamine, and so now more dopamine gets across. Because it binds to this, they call it the presynapse. If we're moving from left to right, and this is the synapse, this would be the presynapse, synapse, postsynapse. Kind of like before the game is the pre-game show, then the game, and then the post-game show, like post-game analysis. So, whenever cocaine binds to this, though, it actually encourages the nerve cells to just like squirt out extra dopamine. It can also damage, it can be toxic to these sending nerve cells, the presynapse. So you can actually damage and destroy these nerve cells. Okay, we said brain and spinal cord nerve cells are not very good at repairing themselves. So when these nerve cells are gone, aren't they gone? We aren't really good at making new ones. And what were those nerve cells for? For feeling happiness. So if I used to have this many of these nerve cells that can make me feel happy, and now I have this many. What does that mean? I just lowered my ceiling for the amount of happiness I could have. In addition, your body just squirted out all of its dopamine. So after you come down off of your high, your body's not releasing any dopamine. There's none to release. Plus your body's like, holy crap, we release dopamine everywhere. Dial it back, slow down with the dopamine. And so now you crash. So a cocaine high doesn't last very long. I want to say, I can't remember if it was cocaine that you snort or crack cocaine, but one of them, the high lasts like 30 minutes or less, something like that. And so after that high, you squirt out all that dopamine, and now you crash. You know, you were sitting at like 100 and of amount of dopamine for happiness. So you take Coke, and so it goes way up, maybe 150 or something. And then the Coke wears off, and now you're cratered. Now you're down to like a 10 or a 20. You just crashed. Well, in theory, your body should just bounce back really, really quickly, but it doesn't. So it turns out studies show that the cocaine brain doesn't recover back to what it was before until about a couple of years later. So here's a normal brain scan, and all those lighted up areas just mean that you have more activity. So red is more activity, yellow is less, green is less, down to the blue. So Roy is more active than G or Biv. So normal brain scan. Here's a cocaine abuser, 10 days after they last took cocaine, their brain is not recovered, which means their brain is still not functioning normally. So they're still addicted, like they still have that craving for cocaine. Here they are 100 days later. The brain is still, that was ecstasy, their brain is still not back to where it was. And so the general idea is that programs where cocaine abusers can abstain for about 2 years, they've got a chance of recovery. Otherwise, they don't. As a general rule, I've heard different numbers, but in general with cocaine, the addiction rate is when somebody tries to stop, about 95% of them fail. So 1 out of 20 people that tries to quit taking Coke is successful. 19 out of 20 are unsuccessful. So you probably shouldn't take Coke. Not only is it messing you up in the moment, but it's also changing your capacity for happiness later. So if I'm functioning at 100, I get high 150, now I recover back to 90. I get high, if I snort the same amount, now I only make it up, right? Originally I was at 100. I snort Coke, maybe, I don't know if it's symmetrical like a line in each nose. So I snort Coke and I make it up to 150, so I went plus 50. Well now, I crash, I come back and now I'm at 90. So now when I snort a line in each nostril, I go up 50. So now I go from 90 to 140. I crash, now my set point is 80. Now I snort cocaine and I make it to 130 and 70, and then eventually my normal is 50. So now when I snort Coke, I just get up to a 100. And this is, I think, I'm assuming the scientific explanation for why drug users will sometimes say, if you ever watch during some anti-drug campaign, maybe they interview a previous drug user, that drug user will say, or maybe on some Netflix special or something, a lot of times you'll hear them say, I first did it for fun, occasionally, and then I got to where I needed it all the time, and I needed it every day. And they'll say this statement, eventually I needed it to just feel normal, to just get up and get dressed, take a shower, and go through my day. Now that means you're so low right here that I've got to snort a few lines to get to a 100. 100 used to just be a regular old Wednesday, right? Back before I was doing all this Coke, let's say, I was at 100. Now I have to snort Coke to just feel normal. So that's scary to me. In addition, kind of like when I mentioned methamphetamine way earlier in the year, it's that whole idea of you could take a pretty normal person, caring, compassionate father or mother that has kids, they would do anything for the kids, get them hooked on meth or some other illicit drug, maybe cocaine, and all of a sudden they'll leave their family. They'll steal from their own family. They'll leave their kids out in the car while they're going and getting high in some drug house. And so to have some powder or some needle, some injection that's got that power over me, it's just scary as heck. I can't imagine how strong that is, that I would blow off my wife or my son. And so that's why I would never mess with drugs. That scares the heck out of me. I never want to be that guy. All right. Thanks for listening. We'll have probably one more nervous system video after this, just to show some, back to the brain, some more interesting things about brains. I don't know if we'll ever get to this part or not. I think I might try to start the next video with that. So thank you very much for listening.